So last time we basically derived our velocity distribution, Vz, for a flow in a tube. That's sort of the most commonly found description in petroleum engineering or any kind of subsurface, well, I would say above surface too. Most of the systems we have, engineered systems, have some tubing that is cylindrical, right? So there's no squares don't behave well. Okay. So we have this, and this is one of the rare cases where I actually have analytical solution, which is very important for any kind of engineering design. We solved for laminar flow in a tube, so that's very important. So I do have to apply that solution, I do have to have laminar regime, otherwise solution is not valid. And we're going to get to what do we do in turbulent, not for a lot, we're just going to actually really mention it in passing, because turbulent flow is an entire semester course in itself. Okay. So that said, one thing that you always have to understand is the limitations of the equations or experiments or both, and how they play together. So I am always supposed to know what's going on experimentally, actually, because I have to ensure that I have a laminar flow before I apply an equation. If I do, I'm going to be off and the flow is not laminar. So there's this cross-check, experimental or what is happening in the actual situation versus what am I solving for. Because mathematical, any kind of mathematical solution is often rather broad, and it applies in some general case. And math doesn't know what you actually have in practice, so you have to kind of constantly go and check. In one case was that when we were solving for shear stress, we got a general form of shear stress, tau RZ, that has a dependence. There's that one term which is something times R, and then plus something times 1 over R. Okay? And that is mathematically correct. Math doesn't know whether actually R is 0 is in our geometry or not. So it's providing us with the general form. But we looked at our tube and said, hey, this is a tube, I have R is 0, I can't have shear stresses blow up. So, not in laminar flow anyway. So basically that constant next to 1 over R has to be 0. So math can't tell me that. I have to look at the situation I have and actually apply the actual boundary condition. Now we will have a case where this R is equal to 0 is not going to be in my geometry. Okay? If I have flow in an annulus, which I often do in practice, okay, I might have a tool in the middle of my wellbore, so I'm flowing around it, that's flowing in an annulus. I might be doing a cementing job, right? So I'm going behind casing, and in between casing and the rock, I have an annulus. Right? So in that case, R is equal to 0 is not part of my geometry, therefore my shear stress can't have that term, and is different. So you do have to kind of constantly walk back and forth between the situation you have and sort of the mathematical description. It'd be very nice just to have mathematical descriptions and never think about anything else, but that's not how life works. Okay. So let's now go back, and now that we solved 2 problems, we're going to look and formalize a little, just like I mentioned, how boundary conditions work and what the rules are. And you had some of that in your homework too. So basically we figured out, so just to recap all of the formulas, and that's also so we have defined Newton's law first in a very simple case where I only had tau yx, but then we generalized it for any kind of flow in any kind of situation, and in that case we have defined our total molecular stresses, which combine pressure, thermodynamic pressure, and viscous shear stresses. And then we also realized, I could actually have things just simply flow in with a different fluid unit, if you will, into my geometry because I'm kind of standing still in a coordinate system. So stuff that flows in is rho v, and it flows in with another velocity, v. So rho vv is our convective stress tensor, and its coordinate description is rho vi vj when I look at the individual element of that tensor. So basically our viscous stress has that cryptic formulation, but that basically describes a Newtonian fluid. I have the Jacobian of my velocity, which is a tensor. So gradient of a vector is a tensor. Gradient of a scalar function is a vector. So go up in dimensionality. And then I have a constant times divergence. Divergence of a vector is a scalar. Divergence, so I have divergence of a vector, but I could also have divergence of a tensor, and that's a vector. Okay? In which case I basically look at all of the, I separate my tensor into column vectors. Choice is mine whether it can really be row vectors or column vectors. And then I work on each of those vectors separately, and I have three numbers that I put together in a vector. So if I'm trying to compute divergence of a tensor, okay, I can, okay, and mathematically I just go column by column and compute all of those individual divergences and put them in a vector. Okay? And that's going to be, I think your mathematical review had something along those lines, right? You're like, now you tell us that. So in your homework, you had something along those lines. All right, so that is just the math review. And then I have identity matrix delta. So this last term doesn't show up often because for the most part, time we're going to be dealing with the incompressible fluids, except for one example that is coming up next week. So in problem solving, we apply shell balances. Basically, I figure out a shell, which is a thin fluid element, okay? And I balance momentum, and by that I mean combined momentum. What can change my momentum? Okay? What can change my momentum is stuff that is coming in or is transferred across the surface of this shell, in or out of the element. Okay? Here we say in and out because we have a clear shell in a coordinate system. But this is really surface integration over the boundary, right? And what is coming in or what is coming out will sort itself depending on what is acting in the normal direction or against the normal direction of that boundary. Okay? So if you think about it, if you have a shell in a coordinate system, then two opposite sides that we call in and out, their normals are pointing in different directions. Like if I look at the outside normal over shell, right? And that's basically what results in this minus. That's why we're applying a minus. Anyway, back to what I was saying. And I could have external body forces working on the element, and that can change my momentum as well. Gravity is one such force. Okay? And then I balance this out. I shrink the shell to a point, and I will get a differential equation that I tried to solve. This differential equation is basically valid in any sort of, in any point, internal point of my geometry of the fluid. Boundary conditions are boundary conditions. I have to apply them on a side in order to solve. So let's comment a little more about, I'm gonna not review now, thin plate. So let's comment on boundary conditions. So if I had fluid and solids boundary, one typical one is that there is no mass transfer through that boundary for obvious reasons. And in that case, I have normal velocity components that have to match. Normal being normal to this boundary. So here's my little solid grain with a normal and tangential component to it. If I have tangential, it's actually a plane, and plane is described with two tangential vectors, okay? And I defined a little local coordinate system next to that boundary. Then if solid is static, this normal velocity will be equal to 0, or otherwise it's matching the velocity of that boundary. When I say no slip, I'm actually looking at the tangential velocity components. And no slip formally means that tangential velocity components of both fluid and solid are equal. And in 3D, for instance, we had a cylinder, right? In that cylinder, right on the boundary, right? My tangential component is this Vz that is, I'm flowing in the same direction as this fluid. So Vz is my tangential component right on the boundary, right? And you were saying, well, Vz is 0 because boundary is static. So that means that those two velocities are equal. So formally, how do I get a component of any vector in direction of a unit vector, any other unit vector? I do a dot product, right? And that's going to give me that component. So dot product basically projects a vector to a vector. And then slip will mean that my tangential velocity is proportional to shear stress, right? So I might have this component that used to be 0 and then plus some beta, which I need to know, times derivative in normal direction of that velocity of the fluid. In your homework, you had a slightly different formulation for slip velocity. Okay? Both are models. None of those models is perfect. If you actually apply this one instead of the one in your homework, you had that you're going to zero out velocity at a slightly different, no, it was B, was the width or half width of your slip. And then you say, well, at B plus lambda, apply this 0. And actually, if you solve the problem this way and this way, it's going to be similar. It's not going to be completely equal, but the solution will be similar. Similar enough to the point that like both, you can tune both to the experiments to be right. Okay? So there's no precisely correct model to apply. It's still just a model. Is that clear? We could have a porous boundary if you end up working in fractured media. Fracture is next to a matrix, okay? And that matrix is typically full of fluids, and we are very much interested in the matrix because that's where the oil is. Everything quickly flows through the fracture, but my business is how do I get into the matrix, because that's where my major storage is in my porous medium that is fractured. Okay? So then you have to actually know what is the transfer and mass transfer across that boundary, and you could specify, and you have to model it often, so you figure out what to specify as a constant flux at the boundary. It's not always known, so you have to play with that and tune to any known information. So those are the fluid-solid boundary conditions. Most often, again, we have no slip. Our boundaries are commonly aligned with a coordinate system, so it's not that difficult to apply. Right. Now, if I have two fluids are themselves like similar, way more similar than fluid and a solid. I will still have no mass transfer for the most part, especially if I have immiscible situation. Okay? So in that case, what that means is that I'm going to apply continuity of normal velocities. So if I have velocity in one fluid and velocity in second fluid, I call them V1 and V2. Right there in the boundary, the normal velocities will be to that boundary will be equal. Okay? So right here, for instance. Now, what no slip translates to is that I'm going to have a continuity of tangential velocities. So again, I have a tangential direction to this boundary, and they're going to be equal. So if I have no mass transfer and no slip, and I'm in a sort of a quasi two-dimensional situation, or even 3D, that's going to be basically once they're equal, that means that the velocities themselves, all of their components, have to be equal if they have to be equal in some coordinate system. And this defines a coordinate system, right? I also have a continuity of shear or tangential stress. So shear stress in one fluid is equal to the shear stress in another. And we did have that situation. So basically we had top of my thin film was essentially, I had to have a continuity of shear stress, but I had air next to a fluid. So basically mu times tau is mu times, let's talk about dv x dy, right? So I'm forgetting, it was x and z, I believe, but now I'm speaking from memory. So let's let those, there's a derivative of, mu times derivative of velocity in one fluid is equal to mu times derivative of velocity in the other fluid at that boundary. Okay? Now, what's key in, if these derivative of velocities are not very large, and for laminar flow, they're not, okay? Then basically what's going to dominate the situation is kind of the difference in these mu's. And for viscosity of air is very small compared to viscosity of fluid, so that viscosity of air is 0, which is how we said, well, shear stress at air-liquid boundary should be 0. Okay? But that's actually a consequence, okay, of this continuity of shear stress. Because basically mu times derivative of velocity in one fluid, okay, is equal to mu times derivative of velocity in the other. And with one of the mu's being really small and going to 0, then basically zeroes out both of those shear stresses. Yes? So that's a consequence of this. Now, if I'm in a situation that I'm at the ocean and it's really, we've had hurricanes blow through, right? So I have shearing at very high velocities. Well, then my velocities are not that small. So even though I have air, right, that equality is not going to necessarily be true. So I don't necessarily apply this zero shear stress situation. Okay. Now, what I could have also is I could have a jump condition for normal stress. If I have immiscible fluid interface, both fluids are kind of pulling away from each other because there are different molecules in contact. Okay? So that's the source of the surface or interfacial tension between two fluids. Okay? And that also allows supporting slightly different pressures. So thermodynamic pressures in those two fluids are different because I also have different molecules moving around, right? Which results in thermodynamic pressure. So in normal direction, I could actually have a difference in the total molecular stress tensor. Again, this is in normal direction. When I do a dot product, I'm projecting something onto a vector. So this is projecting things in normal direction. And in response to these different pressures, my interface will curve. Okay. So curvature cup out that interface. In 2D, if I have a circle, it's simply 1 over radius of that circle. That's my curvature. If I have a sphere or any other surface, I'm going to at every point define 2 orthogonal directions, and I'm going to look at the radii of curvature of those directions and basically find the harmonic aperture. So my curvature, mathematically, you can do that in any point of a surface. Any 2 orthogonal directions will do. It's kind of cool result. But we look at those, what we call principal curvatures, are our extreme values of curvatures for any point of surface. If I have a sphere, it's all great because both curvatures, I'm curving the same way, however I look at the sphere. If I have a straight surface, all great, it's 1 over infinity is my curvature, which is 0. Okay? So straight surface have a curvature 0. The wickedness of 3D is that there is no unique surface. So if you give me a curvature, 0 or 5 or whatever it is, there's no unique surface with that curvature. Sphere is only one of them. So whenever you give me a curvature, I can find a sphere that has that curvature. Right? Curvature is 1 over radius. Just figure out the radius that matches. But that's only one of the possibilities, because I could be curving differently in a different direction. If I have a cylinder, I have a constant non-zero curvature in this direction and a 0 curvature in the straight direction. I could actually be curving completely the other way, which gives me a negative curvature. Right? So I could have a saddle point where one direction is curving this way and the other direction is curving this way. That ends up, if those curvatures are the same in those two different directions, that ends up being a curvature 0. So if I figure out the saddle point that I have curved this way, that one, it's funny surfaces, like they look like a saddle on a horse. So then, because saddle on a horse in direction where you're sitting, it's curved like a horse, right? Which is you can sit. But in the other direction, it's curved like this, right? So you have that saddle point that is going the other way. I just figured out for you the definition of 0 curvatures, like infinitely many of them, because their average curvature, one is positive, one is negative, they'll just cancel each other and be 0. Yes? Is this all too esoteric? The point that I'm making here is that fluid, for a reason, I'm making it for a reason, fluid that enters a porous medium has a lot to play with, given the solid surfaces it can prop itself against. Okay? It can figure out the curvature that you have given the pressures of the fluids, and it can adapt according to it in many more ways than spherical. And that's all I want to leave with you. Now, so basically you have your curvature of the fluid will basically curve in response to this difference in pressures. In tangential direction, we typically ignore this unless you have in tangential direction, sometimes you have a surfactant concentration that changes along tangential direction. Okay? And that can change your surface tension as you go along this direction. There's a Marangoni effect that has some fun consequences because of that. So sometimes you could have, so that's a very complex situation in EOR, okay? That, again, I'm just pointing to some directions of your possible research down there. We're not going to be dealing most of the time, but just understand that if I have two fluids, I don't have necessarily continuity of the molecular stress. I might have a jump. Okay? So different stresses in one fluid versus the other. Most of the time, our boundary conditions are applying continuity of something or the other. But in this case, I could actually have a jump. Specifically because thermodynamic stresses in two different fluids with two different molecules can be different. All right. So for very large tubes or whatever, this curvature of the interface, so if I have very large, since my curvature is 1 over r, at some point r is large enough that I can just zero it out. So I'm not going to have, or I'm not going to account for this jump. Jump exists, but it might be just too small compared to the rest. So if you have larger tubes, you're going to ignore that. If you're inside a porous medium, you have very small tubes, so you can't necessarily.
Dr. Brown,
Yes?
just to make sure, so that equation relates the pressure difference to the curvature of the fluid.
Right, so pressure is built in my molecular stress tensor, right? I have a pressure plus shear stresses.
Right.
So these are the difference between the two is related to the curvature of the interface. So basically, interface curves in order to support that jump. That's why it's curved.
Okay.
Right? So basically, it curves to balance things out at that interface.
So an implication would be that if the pressures are the same, there will be no curvature.
Yeah.
There's nothing to balance.
Yeah.
Okay.
Is that same as capillary pressure?
Hmm?
Is that same as capillary pressure?
Capillary pressure, yeah, that's typically what's, yes, what I refer, in small capillaries, you're gonna have this situation, right? Yes.
And something like displacing oil with water, let's say that you're moving in saturation from high to low saturation. Would you be changing the boundary condition from, like, as you move from continuity and stress, and then when you get to like residual, you get to.
So when you're moving in a capillary, that's this capillary existence. So there's a capillary pressure that you have to overcome, right? And capillary pressure is difference between these two pressures, P1 and P2. Right? So because of that, right, the interesting consequence is when you're moving, you're pushing through. If you're in a tube, the same way you push in is the same way you come out. But if you're in a more complex porous medium, which we always are, right? If we're actually inside a porous medium, then the way you move in, on the way back, all I'm saying is that interface will curve in response to the required. So you are changing pressure from the outside. You're either increasing pressure moving in or decreasing pressure moving up, right? When you're draining or imbibing. Well, on the way back, given the complexity of surfaces, fluid will figure out some other surface with some different curvature, right, to balance these things out. Different from the one that was coming in. In this geometry, I have only one possibility. Right? And that's the whole complexity of via retrapping fluids in porous media. Fluid figures out some other configuration, and that configuration might snap off some blobs of oil that I care about the moment they're snapped off, or it could be some sort of environmental engineering. It could be any kind of non-aqueous liquid that is contaminant in the soil, right? So water is the one that typically easily moves around and it can actually snap those off, precisely because this all just says that the curvature of the fluid will balance it out. And we know we don't have a unique solution to this. So on way in, I figure out one solution. On way out, I figure out the difference. The difference is my difference in pressures versus saturation curve, right, in a porous medium. So essentially, capillary pressure saturation curve is not unique because of that. It's actually not a functional relationship. Right? I have one more thing that I didn't account for, right, which gives me uniqueness. It would be some sort of surface in 3D if I looked at it. And there was now a whole lot of research. One is you have to add area in between the fluids to get an actual functional relationship. But not only area, also number of disconnected components. So sort of like account for the topology of your, both the interface and the actual fluids inside. Now I went off into tangential direction away from our what we're supposed to talk to, but I was prompted, and that's something I care about, so I can talk about it a lot. All right, so we have solid fluid and fluid-fluid boundary conditions. If I rambled about something that you couldn't quite follow in the last 10 minutes, just forget about it. But remember how we assemble boundary conditions. All right. Now let's get back to our discussion, and now we will add. We're not going to work with two fluids. If you want a simple two-fluid situation, I guess there's a solved example 2.5, but it's a very simple, straight boundary between two fluids. So that's not too difficult to work out. It's just maybe hard for that experimentalist in the lab to actually figure out the straight surface across the geometry, but I'm going to leave that to experimentalists, okay? So, assuming a straight boundary between two fluids, you can figure out how to solve that situation in BSL 2.5. Let's now actually move to non-Newtonian fluids. So let's throw in another wrench. And before we move, I'm just going to recap the cylindrical coordinate system and the equations that came up in our during the office hours that I think are very useful to go back and forth. Right? So all those formulas I gave you, the shear stress formulation, it didn't actually have coordinate system attached to it. We typically pick a coordinate system and then I represent my shear stress tensor in that coordinate system. But the generalized Newton's law is valid regardless of the coordinate system. Okay? So that's our local choice. Good news is that whichever choice you have, you can go back and forth. Okay? So if I had, these are my identity or the coordinate vectors in r, theta, z. Okay? So I will have my x, y, z at every point. Okay? This point is just this point. I choose an origin. And then with respect to that origin, I can look at the Cartesian coordinate system in which I have x, y, z, three simplest orthogonal coordinates. But I can also look at the cylindrical coordinate system. So I can look at the distance from the origin, which is r. Okay? I can look at I have x coordinate axis, and I can project this distance, let's call this 0, 0 to p. I can project it down to xy plane and look at the theta that this line encloses with x. And in that world, this is little right triangle. I know my Pythagorean or my basic trigonometry. Basically, my x coordinate is r cosine theta, and my y coordinate here is r sine theta, and z is equal to z. So that's what relates to coordinates x, y, z. But for any vector, if I have a vector representation in one coordinate system, I can go back and forth basically with these two sets of equations. This is basically your r, theta, z coordinates, and you can treat delta x, delta y, and delta z as x, y, z coordinates of a vector. And what this is, there is a matrix with elements cosine theta, sine theta 0, minus sine theta, cosine theta 0, 0, 0, 1, that multiplies this vector in x, y, z coordinates to give you the vector in r, theta, z. So there is basically a matrix that goes between vector representation in one coordinate system and vector representation in the other coordinate system. Vector itself is the same vector, right? It's just how do I view it? Okay? Do I have my glasses on or not? Pictures are different, okay? In terms of actual numbers of what I see, pictures are different. Okay? So I have a translation matrix that goes between view in one coordinate system and view in the other. That doesn't change the object I'm looking at. Okay? Now I can go back, and actually if you look at this as a matrix with 3 by 3 matrix that goes between this vector and that vector, this matrix here is transpose matrix here. And if you multiply the two, you're going to get identity, by the way. That's just the rule for whenever I have two orthogonal coordinate systems and go back and forth. So if you remember the one, or write down the one, you can write down the other just by transposing here. You have minus sine here, sine here, sine here, minus sine here. Okay, so when I look at the coordinate system, right, when I look at my one little element, what's important to note is that if I have, this is my point r theta z, okay, I have some dr in radii, and I have d theta, okay, and you can figure out that basically the length of this here is r d theta. And the z, so basically I have this sort of, it's a curved box. It's not completely straight. So when I integrate, I have to take that into account. My volume integral, for instance, is not going to be dx, it's not going to be triple integral and then dx, dy, dz. It's going to be triple integral with my r, theta, and z going over whatever ranges. Dr, r d theta dz. Okay, because I have a curved coordinate system and I have to account for that. basically this is my volume of this little element here. Okay? So when I have a volume integral in these coordinates, I'm going to have to stick in an r here. Okay? So dr, rd, theta, dc. And same if I have integral, area integral going over r and theta. Okay? So we had our momentum equations for laminar flow in the incompressible fluid. Okay? We got a general z momentum balance. And if you remember, this is its general form. I just put this as area in r, which is a function of r. Okay. And that resulted when I divided by my volume and actually put in what this area is, I have an r as a remnant of this area that changes. Okay. So this is my general z momentum form. It's a differential equation. I did not define what my fluid is, so this is valid for any fluid. Okay. And any force. Okay. So here I have gravity force, technically with the dot product here. Okay. Technically, I should actually put this as the FGZ, as in this is the z component of it, projected z component of it. So this is also general for any body force that is working on the fluid. Now, if I had a horizontal flow, okay, this z, this dot product here, component of horizontal flow would be 0, so I would just have, if I had a horizontal tube, this would be 0, right? So if I understand this as a z component of whatever body force, then this is generally valid for any type of tube alignment. Okay. So if I had tube that is tilted, right, then I could do a dot product and figure out what is the balance for in that tilted direction, if that tilted direction is my z direction, right? So I can apply this more generally just with the understanding that I'm going to take the component of the force acting in the direction, if it actually acts in that direction. If it doesn't, my projection is 0. Okay? All right. So this is pretty general. Yes, questions?
If we have a horizontal flow, don't we have a body force in terms of, so FGR? So
You do, we ignore it. Okay? Because I don't have boundaries that are open in that direction, so it's not going to really flow in that direction. Right? I can't go through if the boundary is closed. So that's a dominant effect for smaller tubes. Okay. For larger tubes, it's not. I might still ignore it in order to calculate. Okay. But then I have an approximation. My solution is always an approximation, and that approximation works better in some cases than the others. All right. So this is my Newtonian fluid in a tube. So for Newtonian fluid, I know what phi is, and I have an expression for it. Okay? And if I have cylindrical coordinates, I need to use this in cylindrical coordinate system. And for all kinds of, if in case you need, there is like an entire table for cylindrical coordinate system, how do you calculate divergence gradient and all that stuff in the back of your BSL. All right. So this is what we calculated for Newtonian fluid, and we're about to discuss what's different for Newtonians. But before I go there, just as a recap of these coordinate systems, so how would I calculate volumetric flux through this tube? I'm sitting here with a little bucket. All I can measure is my flux, volumetric flux per second. That's all I'm measuring in the lab. So I need to match the two. Okay. What will I integrate? How will I get that?
double integral of the cross-sectional area of the fluid flows.
Okay. So my cross-sectional area is down here. Okay. Double integral is over which two coordinates? R and technically theta, right? Though it's in this case it's a projection, so it's trivial. So I'm gonna have, but I do for volumetric flux, if I'm back to my three-dimensional world, I do have to account for it. So I'm gonna do integral over r and theta, okay, of Vz of r, and my element area is r d theta, okay, because I'm in cylindrical coordinate system. If you forget that, or just put in your mental note to look up that formula, it's actually, I took this from the appendix. So back in appendix 6, you will have also how to do area integral in cylindrical coordinate system. So don't forget that r d theta, okay? And that's because of this little curved element has slightly different area than it would in Cartesian coordinate system. So again, I integrate this b rz of r with respect to r and theta, and I have to remember that the area element is r d theta. Okay, cool. So what about non-Newtonian fluids? So Newton's law basically says that for Newtonian liquids, I have this simple relationship between my shear stress. If I'm back to my tau yx situation, I have tau yx shear stress, and I have gradient of, or derivative of velocity, and I have a simple linear relationship between the two, and it basically just defines the coefficient of proportionality mu to put in that. Now, many industrial liquids will have some polymers or solids within, and they behave somewhere in between fluids and solids. And we have to account for that. And there's, rheology is a science that basically studies this deformation and flow. It's mainly concerned with liquids and soft solids, because solids themselves might not deform enough to actually flow in any matter. Oh, wow. Okay, I'm out of time. So we're gonna continue this. Good news is we already watched that movie of Ellen DeGeneres of shear thickening fluid and cornstarch. You can watch it again. But we're gonna continue, and then we're gonna actually solve for Bingham flow in a few. Your next homework will be assigned on Monday, okay? And it'll be then due Monday after that, okay? I know that you would otherwise be bored, so I gotta give some more homework. Right?
Why in this case?
Well, let me just stop recording.